For more than a century, humanity has looked into space with a mixture of awe and curiosity, discovering the secrets of the universe one by one. In recent years, however, an unexpected confusion has cast a shadow over our understanding of the cosmos. A deep and perplexing question arose that challenges the foundations of cosmology. How fast is the universe expanding? This seemingly deceptively simple question has led to one of the most heated and intractable debates in modern science. Cosmology, the study of the origin, evolution, and ultimate fate of the universe, is at a dead end. The crux of the matter lies in controversial measurements of the expansion rate of the universe, known as the Hubble strain. During more than a decade, the two main methods of measuring expansion were in conflict with each other. One method of studying the current universe suggests that the universe is expanding about 9% faster than predicted by observations of the early universe. This difference has confused scientists and caused heated debates in the scientific community. The arrival of the James Webb Space Telescope, JWST, the most advanced and powerful telescope ever built, was to settle this dispute once and for all. New, incredibly precise JWST measurements, launched in the hope of clarity, have added to the confusion. Detailed observations from the telescope confirmed a faster rate of expansion, further challenging the standard model of cosmology and leaving scientists in disbelief and wonder. The standard model, known as the lambda cold dark matter lambda CDM model, has been a cornerstone of cosmology for decades. It elegantly describes the composition and evolution of the universe and predicts its behavior with remarkable accuracy. However, Hubble's continued excitement suggests that there may be a fundamental part of the universe that we still don't understand. As scientists dig deeper into the JWST data, it becomes increasingly clear that there is something fundamentally wrong with our understanding of space. Our journey to the heart of this mystery begins with the Big Bang, the massive explosion that marked the birth of the universe. About 13.8 billion years ago, energy, mass, and space erupted in an instant with unimaginable intensity. After the Big Bang, the universe was a boiling, expanding plasma filled with particles of matter and antimatter that annihilated each other when they touched. Despite this chaotic beginning, a slight imbalance allowed matter to dominate antimatter, laying the foundation for the universe as we know it. As the universe expanded, gravity began to act, squeezing out pockets of plasma and creating sound waves known as baryon acoustic oscillations that rippled through the early universe. These oscillations left their mark on the cosmic microwave background, CMB, which is the afterglow of the Big Bang and provided a snapshot of the universe when it was only 380,000 years old. By studying the KMB, scientists can infer the conditions of the early universe and calculate the expected rate of expansion. Measurements of the CMB, made mainly by the European Space Agency's Planck satellite between 2009 and 2013, suggest a Hubble constant of about 67 kilometers per second per megaparsec, km/s/mpc. This means that for every megaparsec, about 3.26 million light-years away from us, the galaxy appears to be receding at 67 kilometers per second due to the expansion of the universe. This value derived from the early universe was a key component of the lambda CDM model. In contrast, measurements of the present universe using Cepheid variables and type I supernovae give a significantly higher Hubble constant of about 73 kilometers per second per MPC. Cepheid variables are pulsating stars that vary in brightness in predictable ways, allowing astronomers to determine their absolute brightness and thus their distance. Type I supernovae, which are the thermonuclear explosions of white dwarf stars, also serve as a reliable distance indicator because of their constant peak brightness. Methods perfected over decades provide a solid framework for measuring cosmic distances and expansion rates. The higher rate of expansion observed in the present universe gave rise to the term Hubble tension, reflecting the tension between these two conflicting measurements. The implications of this difference are profound, suggesting that there are unknown systematic errors in one or both sets of measurements, or that our understanding of the universe is fundamentally flawed. This has led cosmologists to explore a variety of possible explanations, from new physics to exotic forms of dark energy and matter. One of the more interesting possibilities is that dark energy, the mysterious force driving the accelerating expansion of the universe, may be behaving differently now than in the past. The simplest explanation for dark energy is that it is a cosmological constant, a form of energy that travels through space uniformly and remains unchanged over time. However, if the properties of dark energy have changed during cosmic history, this could explain the different expansion rates. This hypothesis led to many theoretical models and extensive observational efforts to test its validity. Another line of research is related to the nature of dark matter, which makes up about 25% of the energy mass of the universe. Dark matter does not interact with light, so it is invisible and detectable only through gravitational effects. If dark matter has properties or interactions that we have not yet discovered, it could affect the expansion rate in ways that are not accounted for in the lambda-CDM model. Some theories suggest that dark matter may interact with photons or other particles in subtle ways that may alter the observed rate of expansion. Despite these interesting possibilities, no definitive explanation has been found. JWST observations only deepen the mystery, revealing early galaxies that are much more massive and mature than expected. According to the standard model, the first galaxies should consist mainly of young, hot stars that formed quickly. However, JWST discovered galaxies full of heavy elements and active supermassive black holes, challenging our understanding of galaxy formation and evolution. The stakes in solving the Hubble tension are high. If the difference persists, it may signal the need for a paradigm shift in cosmology, similar to the changes brought about by the discoveries of dark matter and dark energy. As scientists continue to analyze data from JWST and other observatories, the cosmological community is divided into camps seeking very different solutions. Some researchers focus on identifying possible systematic errors in the measurements, while others develop new theoretical models that could reconcile the conflicting expansions. The path to a solution will likely involve a combination of these approaches. Continued observations of JWST, along with other future telescopes such as the Nancy Grace Rome Space Telescope, will provide more detailed information and possibly new insights into the nature of dark energy and dark matter. At the same time, advances in theoretical physics may provide new explanations that are consistent with observations. Hubble's excitement is a reminder of the ever-evolving nature of science. Each new discovery opens the door to new questions and drives the relentless search for knowledge. As we stand on the brink of potentially revolutionary changes in our understanding of the universe, the excitement of the scientific community is palpable. The journey to unravel this cosmic mystery is far from over, and the discoveries ahead promise to shape our understanding of the cosmos in ways we can hardly imagine. This journey to the unknown recalls the great scientific revolutions of the past. When Galileo first pointed his telescope skyward, he revealed a universe far more complex than previously imagined. Similarly, Edwin Hubble's discovery of an expanding universe fundamentally changed our understanding of cosmology. Today, we are on the brink of another profound shift that could redefine our place in the cosmos. As scientists sift through the JWST data, they are also re-examining the fundamental assumptions of cosmology.
One such assumption is the unity of the universe on large scales, known as the cosmological principle. This principle requires that the universe be homogeneous and isotropic, which means that it looks the same in all directions and places. However, recent observations have hinted at the possibility of large-scale anomalies, such as cosmic voids and superclusters, which could affect the measurement of the expansion rate. Furthermore, the interaction between dark matter and dark energy remains one of the greatest mysteries of cosmology. These two components dominate the mass-energy content of the universe, but their exact nature and relationship are shrouded in mystery. Some theories suggest that dark matter and dark energy may interact in ways we have not yet observed, affecting the expansion of the universe in unexpected ways. Unraveling this interaction may hold the key to solving the Hubble tension. Efforts to understand the expansion rate of the universe also intersect with cutting-edge research in particle physics. The discovery of the Higgs boson at the Large Hadron Collider, LHC, opened new avenues for studying the forces of nature. Some physicists speculate that the cosmic expansion may be influenced by unknown particles or forces. For example, the concept of dark radiation or other types of neutrinos could change the dynamics of the early universe and reconcile conflicting measurements. Theoretical physicists also study changes in general relativity, Einstein's theory of gravity, which supports our understanding of cosmology. Alternative theories of gravity, such as modified gravity or scalar tensor theories, could provide a framework to explain the different rates of expansion. These theories indicate that gravity behaves differently on cosmic scales, which can affect the expansion and structure of the universe. The role of advanced technology in the midst of this research cannot be overstated. JWST represents the pinnacle of human technology designed to observe the universe with unprecedented precision. Its ability to peer into the distant past and capture the light of the earliest galaxies provides a unique window into the formative years of the universe. As more information becomes available, scientists hope JWST will provide the clues needed to resolve Hubble's tensions.